Hello everyone, welcome to this video. In this video, we are going to learn about the liquid state machine using OpenMathAI. So, let's get started. What is a liquid state machine? A liquid state machine is a type of spiking neural network used for temporal data processing, pattern recognition, and prediction, unlike traditional neural networks, which process continuous numerical values directly. An LSM processes information through spike-based neuron activity. An LSM mainly consists of an input layer, a randomly connected spiking reservoir called the liquid, and a readout layer. The input values are converted into spike signals and passed into the liquid. The liquid transforms these signals into complex dynamic states, and the readout layer uses these states to calculate the final prediction. During prediction, the input signals activate different neurons inside the liquid reservoir. The reservoir captures nonlinear relationships and changes in the input data, while the trained readout layer converts the reservoir activity into the predicted output. We will use a radar target prediction dataset for the LSM model. This dataset contains 500 data samples. The target class probability depends on the nonlinear relationships between the radar signal characteristics and the target's velocity. During training, the LSM transforms these input values into spike-based reservoir states and trains the readout layer to predict the target probability. Once the model is trained, OpenMathAI uses a learned reservoir dynamics and readout parameters to predict the target class probability for new radar measurements without retraining the model. So, let's get started. Open OpenMathAI. Click Create New Project. Enter the project name as LSM. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for Dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Enable the dynamic case states, because LSM is a dynamic model. Configure the dataset by specifying the inputs, feedback states, and targets. There is also a feature called Ignore, which can be used for columns that should not participate in model training. Feedback allows the previous reservoir state to influence the current state, enabling the LSM to remember recent information. This short-term memory helps the model capture temporal dependencies and improve predictions for sequential data. Select the input and output columns manually or use Smart Suggest for automatic recommendations. There is one more feature is signal diagnostics. There is a free columns. First one is column its tell which features on the dataset like inputs and outputs name. Second one is VIF if it tells how much correlation of the features. Third column is status if it's okay, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the LSM model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Train Models. Review the training configuration, test data split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. And also another feature is added that is train from scratch or continue from use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R-squared measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from tricks such as R-squared, RMSE, and residual errors. Model accuracy is commonly estimated using the R-squared value. Example, R-squared equals 0.95 accuracy almost equal to 95%. Click Fit to Window. You will see 3 types. Fit to Window, comfortable, compact. Then the Clear History. If you click that, it will clear the history before its trained model. Another is Deselect and select all trained model for export. Click View Curves. You will see the diagram of parity, residuals, and residuals histogram and predicted output. Click Math and Code Preview to view the mathematical model generated by OpenMathAI, the complete liquid state machine architecture, generated source code, and training details. Open the Math view to visualize the complete LSM model. Maximize the window and scroll down to see the input layer, recurrent reservoir with 220 spiking units. Readout layer, output prediction, the feedback recurrence path, and the complete network structure. The visualization shows how the input features are transformed into dynamic reservoir states, processed through a recurrent spiking reservoir, and passed to the readout layer to generate the final prediction. The input layer receives the scaled input features and sends them to the recurrent reservoir, where 500 spiking neurons process the information and capture temporal patterns through recurrent connections. The readout layer combines the reservoir states with the current input features to generate the final prediction. The skip path provides a direct connection from the input to the readout layer, while the feedback recurrence path preserves short-term memory by allowing previous reservoir states to influence current processing. After training, OpenMathAI uses a learned reservoir dynamics and readout parameters to predict outputs for new input data without retraining the model. Return to the result page and click Deploy Status. Click Export Model. Choose the required export format: ANSI, MCU Fixed Point C, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these formats and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.